Alright everybody, welcome back to Waves and Sound. We're doing some honors-based problems here. We're going to be talking about standing waves. It's going to be a little bit complicated, but hopefully shouldn't be that big of a deal. Alright, so a lot of information at the beginning. What do I want to say about standing waves? I don't know, maybe we'll just go into it. Okay, so a standing wave is a pattern that results from the interference of two waves with the same frequency, amplitude, and wavelength traveling in opposite directions. In a standing wave, certain points, nodes, remain stationary, while other points, antinodes, oscillate with the maximum amplitude. You guys probably don't know what's being said at all. But a standing wave, a lot of time, especially with the problems that we're going to be doing, if there's going to be a wave and it's going back and forth like this, and it's going to be going back and forth like this very, very, very quickly. Okay, that's all I want to say for now. A wave reaching the end of its medium, but where the medium is still free to move, will be reflected and is reflected to be upright. So what that means is, that's going to be kind of like the option B right here. Oops, sorry. So when this wave travels, it's going to travel down this way. It's going to hit the end over here. And then when it hits the end, it's actually just going to be reflected back going like that. Okay, we're not going to be really dealing with waves that move like that, but just know that. When there's a free end, there's nothing holding it back. It's just going to be reflected going back in the same upright position. The other wave, which we're going to be seeing more, a wave hitting an obstacle will be reflected and its reflection will be inverted. So if we're looking over here, this wave is going this way, and then it hits this place where it stops. It makes it stop. And then what happens is it's reflected back, but this time it's reflected back on the other side. Okay. And this is what we're going to be talking about. We're going to be talking about waves that are between 2 points, and they're going to be oscillating back and forth. And then as they hit this side, they're going to be going down the other way. And it's going to be creating this kind of like interesting pattern. Like that. Like that? No, not like that. Sorry, I should draw it better. Okay, so there's going to be like 2 points. And what's happening is we're going to have a wave traveling like this. And it's going to be hitting this. And then it's going to be reflected back going like this. Okay. And when it's going back looking like that, what's going to be happening is it's going to show us a few things that we're going to be talking about in future slides. But it's going to be looking something like that. Highly suggest watching this video to understand more physically what I'm talking about, but these videos really help with that. Okay, so what's going to be happening is as the waves are kind of moving back and forth between these two barriers, standing waves are formed due to constructive and destructive interferences of two waves traveling in opposite directions. So some are like going up while some are going down, and then they're going to be creating this constructive and deconstructive kind of waves. And what's going to be happening is it's going to be looking like there's going to be certain points where it's going to be totally destructive, like here, and here, and here, and here. And then constructive, like here. Okay? So the points where it's totally destructive, I'm going to be circling. I'm going to use a different color. Totally destructive, here, 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 and here. Those points we call nodes. Nodes are points where the wave amplitude is 0, result from destructive interference. Antinodes are points where the wave amplitude is a maximum, results from constructive interference. So antinode. Okay, there. Stationary appearance. Unlike traveling waves, standing waves appear to oscillate in place without moving through the medium. So even though they look like they're not moving, they're moving actually very, very quickly, and then it just gives us this pattern that looks like it's not moving. Okay, if you looked at the videos, you'll be able to see the pattern, but what's happening is it's just oscillating back and forth very quickly. Okay, moving on. Again, good video with notes. All right, harmonics. So in standing waves, refer to specific patterns of vibration that occur when a wave resonates in a medium, such as string or air column. Each harmonic responds to a unique frequency at which standing waves can form, depending on the medium's length and boundary conditions. Fundamental frequency. So what this is saying is, okay, we have a standing wave, right? And the faster the frequency is, the more it's going to look like this. While the slower the frequency is, the wavelength is going to be elongated. It's going to look something like, maybe it'll look something like that. So the fundamental frequency, the first harmonic, is the lowest frequency at which a standing wave can form. For a string fixed at both ends, that wave has one antinode in the middle and two nodes. So the fundamental frequency is going to have on the first harmonic is just going to look something like this. It's going to go like this and like that. And when it hits this part where it can't move, it's going to go back on the other way like this. So it has one antinode right in the middle right there. That's the highest point. And nodes at each end. So there's a node right here and a node right here. Two nodes. Okay? That's the first harmonic. Higher harmonics, each harmonic represents a higher frequency standing wave pattern. The second harmonic, first overtone, has two antinodes and one node between the fixed ends. So how that's going to look like is, let's say, okay, and it's going to be reflected back. And then we see two antinodes, and then three nodes. 1, 2, 3. Okay. And as the frequencies get higher and higher, there's going to be more antinodes and nodes and things like that. We'll talk a little bit more about this soon. Okay, so here is the formula that we have, standing waves formula. So the wavelength to the nth harmonic, so depending on what the frequency is equal to twice the length of the medium. A lot of times, for at least now, we're going to be talking about the length of the string, but whatever the medium is, divided by the harmonic number. Since we're just talking about an easy way when we're doing standing waves is the harmonic number is going to be equal to the amount of nodes. So the first harmonic is going to have one antinode, so this n is just 1. The second harmonic is going to have two antinodes, so that will just be 2. The third harmonic will have 3 antinodes, so that'll be 3, and so on and so forth, okay? Again, here's the formula, and here's how to manipulate the other variables as needed. All right, moving on. How many nodes, including endpoints, are in the third harmonic of a string fixed at both ends? Okay, third harmonic. So if we look back over here, we can see a third harmonic has 3 antinodes. Okay. Oops, sorry. So here we go. It's going to look something like, pretty much like that. Let me change this. Not the best at drawing, as you guys all know by now. And then it's going to go back the other way. So, how many nodes, including endpoints? Oh, so 1, 2, 3, 4. 4 nodes and 3 antinodes. Okay. All right, moving on. Looking at the diagram below to the right, what is the number of harmonics and the wavelength? So remember, standing waves, all we need to know is how many antinodes there. 1, 2, 3, 4. So number of harmonics, fourth harmonic. What is the wavelength? So 2 ways we can do this. First of all, we should know the wavelength is where we can go from where it starts here, and then when it goes through a full cycle. So that's going to be the wavelength. Okay, and in this case, that's going to be half of the length of the string. So this is going to be 2.5 meters. Okay, that's the answer. We could just do that to figure it out. But also, we know that the formula, the wavelength to the nth harmonic is equal to 2L divided by n. So the length of the string is 5. N is the number of a harmonic, which is 4. So then this is going to be 10 divided by 4, which is also 2.5. Okay, the wavelength 2.5 meters. Okay, so 2 ways you can figure out what the wavelength is for this problem. All right, moving on. For a string vibrating in its second harmonic, how does the wavelength of its harmonic compare to the length of the string? Okay, so second harmonic is going to be 2 antinodes. So 1. Okay, that's how it's going to look. And then it's reflected back. Okay. So we can see here, this is the equivalent of a wavelength. So this wavelength and length are the same in this instant. Okay. So it's just going to be equal to each other. All right, moving on. Looking at the diagram below, if the wavelength is 0.8 meters, what is the length of the string? Okay, so the wavelength, starting from here, cycling all the way through, that's going to be 0.8 meters. Okay, so we could kind of use this and use math knowledge to figure out, what this is. But I'm going to use the formula that was given to us. Wavelength to the nth harmonic is equal to 2L divided by N. And what are we looking for? The length of the string. Okay, so I could do wavelength nth harmonic times N divided by 2 equals L. Okay, so wavelength is 0.8. N is 1, 2, 3, 4, 5. And then divided by 2 equals L. And then let's put this into our calculator. 5 times 0.8 divided by 2. And we get 2 meters. Okay. So 2 ways. Then we could also say, like, okay, this is 1.6. And then this is going to be half of it, 0.4. And that also equals to be 2 meters. Okay. All right, moving on. What is the amplitude of a standing wave at its node? Okay. So let's just kind of draw something out here. We'll draw it like this. Okay. So the node is right here. And we can see at the node, there is no amplitude. It's right at the center point right there. So there is no ode. There is no amplitude. The amplitude is just going to be 0. All right, example number 6. If the following diagram shows waves moving at 8 meters per second, what is the frequency of this wave? A few things going on over here. So we have giving us a wave speed. So we should remember the formula. Velocity is equal to the wavelength times the frequency. Next thing is we have the length of the string over here, and this will probably help us find what the wavelength is. So we need to find what the wavelength. A few ways to do this, but I'm going to do wavelength N is equal to 2L divided by N. And let's see how many harmonics. This is going to be 5th harmonic. So 2L, which is 10, 5th harmonic. So this is going to be equal to 4 meters. So now I could figure this out. Frequency, manipulate this a little bit, is going to be equal to velocity divided by wavelength. Velocity is given to us, 8 meters per second, divided by the wavelength, which is 4. So the frequency should be 2 hertz. Went through that a little bit fast. Maybe watch it again if it was a little bit too fast. This was a little bit more complicated than the ones we've done so far. So make sure if you watch it again if it was a bit confusing. But that's what we have, 2 hertz. Okay, we're going to do, in a standing wave, what type of interface causes nodes to form? Again, the nodes are these points with 0 amplitude, and what causes them to form is the destructive waves, interferences with each other, which we talked about prior. Okay. A string fixed at both ends is 2 meters long. If the speed of waves on the string is 40 meters per second, what is the fundamental frequency? Okay, so we should know that the fundamental frequency is going to look something like this. Sorry, my bottom part did not look so good. The fundamental frequency is like this. Okay. Okay, a few things. Velocity is equal to wavelength times frequency. And then what are we looking for? If the speed of the wave is 40 meters per, what is the fundamental frequency? Okay, so we're looking for what this, no, not the wavelength. We're looking for what the frequency is, okay? So both ends, we know the length of the string is 2 meters. But we don't know what the wavelength is. Well, we could easily figure it out because we know that this is half a wavelength. And if this is 2 meters, then we can figure that out. But let's use the formula. Wavelength to the nth harmonic is equal to 2L divided by n. This is the fundamental frequency is the first harmonic. So wavelength n, 2L, L is 2. And since this is the first harmonic, this is 1. So this is equal to 4 meters. Now that we know that, we should be able to find the fundamental frequency. That's going to be equal to, do some manipulation, velocity times the wavelength, or divided by the wavelength. And velocity is 40, wavelength is 4. So this should be 10 hertz. Okay, another one that's definitely more on the trickier side. So watch again if it didn't make too much sense to you or if it was difficult. But that's pretty much it. All right, thanks for learning about this. Standing waves, a little bit of a harder part of this chapter, but hopefully it's fine for you. Thanks for watching, everyone. Bye.